Oh, hello. I'm sorry. I have found the wrong link and I tried to uh, join to another conference. So there was some problems with my Zoom account. Now it's okay. I hope you can hear me. Yes?
Yes, we can.
Okay, thank you very much. And first of all, I would like to say that we have an extra seminar tomorrow in the morning at 10:30. It's not my decision. We are to do this seminar, and because of there was some previous gaps when uh, just uh, not non-working week and so on. So we are to have extra seminar, but we have not extra lection. Um, we have extra lection, but it's just a consultation. So I hope that we can just solve all the tasks for today during these two seminars, and I hope we would have a comfortable temp and we understand all the tasks during two seminars, but not one. Okay, and uh, I have sent you this sheet with problems to your group email. Have you find it? There is no this paper on wiki, but there is on your email. Okay. Uh, I hope you receive my letter. So let us start. And the first question is we have G as follows: x plus y and z plus w. This is a subset of polynomial ring in 4 variables. And we need to show that G is a Grosvenor basis for any lexicographical order. Okay, let me remind you what is lexicographical order and what is Grosvenor basis. If I have, oh, I have a problem. I can't write. Oh, it's okay. If I have n variables, x1, x2, and so on, xn, then I want to fix ordering on these variables. For example, the standard ordering is that x1 is bigger than x2, is bigger than x3, and so on, is bigger than xn. And if I fix this ordering, then I can describe the lexicographical ordering on the set of monomials. This is for this ordering of variables, the lexicographical ordering is standard. So if I have this one and one more monomial with powers b1 and bn, then first of all I measure A1 and AB. If A1 bigger than AB, then the first monomial is bigger. If B1 is bigger than A1, then the second monomial is bigger. If they are equal, then I look to A2 and B2, and so on. If I have another ordering of variables, for example, I say that x2 is bigger than x1, is bigger than x3, and so on, is bigger than xn. Then when I have two monomials, x1 in power a1, x2 in power b2, and so on, xn in power bn, and oh, why b? I'm sorry. Here all the powers are a, and b is the powers of another monomial, x2 in power b2, and so on, xn in power bn. Then first of all, I look to a2 and b2 because I have that x2 is the biggest variable. So first of all, I see to the powers of the biggest variable. If they are equal, then the next one is x1, and on the second step, I look to a1 and ab. But if a2 is bigger than b2, then first monomial is bigger than the second, and it is not depend on a1 and a b1. Okay, I hope it's clear. Yes? Is it okay? We have many lexicographical ordering. If I fix the ordering on the set of variables, then I have corresponding lexicographical ordering for monomials. It's clear?
It is.
Okay, thank you very much. And let me remind what is the Grosvenor basis. If I have an ideal I, sometimes I have some basis of this ideal. More convenient to say that I have the set of generators of this ideal f1, so on, fk. Then I can take an element g on this ideal I if and g can be reduced by some number of reductions by, for example, f2, so on, fs, to some remainder. And if f1, fk, this is a Grosvenor basis, then r is always 0. So f1, fk is a Grosvenor basis if and only if for every g from I, its remainder for any uh, reductions, the remainder is 0. If for any element g from I and any set of reduction, the remainder is not 0, then this is not the Grosvenor basis. And how can we check that this is the Grosvenor basis? We need to construct S polynomials. Let me remind what is S polynomials. So we have f1, so on, fk. Now I fix I and g. This is indices among 1 and so on k. And I want to construct S a polynomial of fi and fj. First of all, I need to compute the leading term of f1 and the leading term of I'm sorry, not f1, fi and fj. These are monomials. And now I can compute the I have a little bit problem. In Russian, it's наименьшее общее кратное. In English, it's lowest common multiple, LCM, yes?
Yes, it is.
Okay, thank you very much. Of these two monomials, L of f1 and L of f, I'm sorry, not one, I and L of fj. It should be mentioned that these terms can be such with coefficient a multiplied by x in power alpha 1, so on x in power alpha n. This is b multiplied by x in power beta 1, and so on, b x, I'm sorry, x1 in power beta 1, xn in power beta n. But the lowest common multiple has no any coefficient. It is just x in power maximal of alpha 1 and beta 1, and so on, x n in power maximal of alpha n and beta n.
I'm sorry, shouldn't it be also a maximum of a and b?
No. What?
No? Okay.
There is no any coefficient here.
All right.
It's not a big deal that there is no, but just let us say that there is no coefficient here. And now S polynomial equals to this one. This LCM of these two guys divided by L of fi multiplied by fi minus this lowest common multiple of these two guys divided by the second L of fg multiplied by fg. This is the S polynomial by definition. And the theorem says that f1 and so fk, this is a Grosvenor basis, if and only if for all pairs I and g, I is not equal to g. We have that S polynomial of fi and fg can be reduced to 0 by some set of reduction of elementary reduction, and this is can be reduction. All the reminders are 0. If we have a reminder for some set of reduction which is not 0, then f1 so on fk is not a Grosvenor basis. If for some set of reduction the remainder is 0 for every I and g, then f1 so on fk is a Grosvenor basis. Okay, let us use this assertion for task number 1. Do you have some question concerning this, or we can start with task number 1? Okay, let us start. And if you have questions, then you asked it after this task. So, okay, we have two polynomials, f1 equals to x plus y, and f2 is equal to, where it is, z plus w. Now we need to compute S polynomials. We have just one S polynomial, S of f1 and f2. Okay, first of all, we need to compute the greatest, the leading term. But in this task, show for any lexicographical ordering, but let us do it for standard lexicographical ordering first of all, and then we can think about any one. Okay, now we have standard lexicographical ordering that x is bigger than y, is bigger than z, is bigger than w. Okay, then L of f1, it is x. And L of f2.
Aren't they G1 and G2? And F should be like a polynomial itself? But whatever. We can use this notation maybe. This would just be a little bit like confusing.
Some problem is
No, just like formal stuff that usually we note the reduction
F
things
is
G's,
any,
and F is what we reduce.
okay, but I have used these notations for in the previous discussion. So let me.
Yeah, whatever. Okay, it's fine.
Okay, and the leading term of f2 is equal to z. Now we need to compute LCM of x and z, and of course it is x multiplied by z. So now we compute this as polynomial. It is equal to x multiplied by z divided by x multiplied by f1 minus x multiplied by z divided by z multiplied by f2. This is just this formula, this one. Here it is. This is the lowest common multiple, and this is leading term of this guy, and multiplied by this. And this is lowest common multiple divided by the leading term of f2, and multiplied by f2, and minus here. Okay. Now we just computed. This is x z plus plus yz minus x z minus x double. And of course, these leading terms are too concrete, so there is no these leading terms. And now we have y z minus x double. Okay, this is the S polynomial, and now we need to reduct it. So we have yz minus xw. How can we reduct it? Here x and z are greatest leading terms. So it's up to us. For example, I want to reduct this term by the second polynomial. Okay, let's do f2. We have this yz minus y multiplied by f2 minus xw. Okay, this is yz minus yz minus yw and minus xw. So this is the result of the first reduction. And the second one, I should to reduct this polynomial. So minus wy minus xw. I should reduct it by the only way by this monomial by f1. So minus wy minus xw minus minus w multiplied by f1. It is equal to minus wy minus xw plus xw, so it's 0, and plus yw. So it's 0. Okay. And now let us say that for any pair I and G, we have just the unique pair. This S polynomial can be reduced to 0. Okay, then this system F1 and F2 is a Grosvenor basis. Okay, we have solved the task number 1 for standard lexicographical ordering. It is clear. Do you have some questions? Just by this algorithm that we compute as polynomials and reduce it to
Shouldn't we check S of F2, F1 is going to be a little bit different? Like up to signs.
S of F2, F1 equals to minus S of F1, F2, and
True.
One can be reduced to 0, then another also. So you shouldn't check just one.
So we've proved it for one Lexis.
Yes, for every pair I and G,
yeah, I see.
You should take either S of Fi, Fg, or Fg, Fi. And the task was not for just for this ordering, but for every. But it is clear that if I replace, remove, don't remove, replace, swap some variables, for example, then F1 and F2 should be the same. So I try to say that if I have another ordering, then situation just the same, but with mm, permuted variables. So of course, if this is a basis Grabner basis of for some ordering, then this is Grabner basis for any ordering. But this situation is not always. This is just because our polynomials are rather symmetrical. But in common situation, if you have a Grabner basis for some ordering, it cannot it can be not Grabner basis for another ordering. Okay, let us proceed with task number 2. We have this system, and we want to do two things. First of all, we want to say that G is a Grosvenor basis for any lexicographical ordering, and we want not a Grosvenor basis, I'm sorry, and we want to apply the Buchberger algorithm for standard lexicographical ordering. Okay, let me remind what is the Buchberger algorithm. If we have, okay, let me change my notation because in lectures I say I think was G, so we have G1 and Gk. This is the system of some polynomials. These polynomials generate the ideal I. So now I want to construct the Grosvenor basis of this ideal. How can I do it? I compute S polynomials, and I try to reduct it by G maybe S, so on, GL. I reduct it to some remainder R. If this R is not 0, then I should add it to my system, and I correspond this system G1, so on, GK, and R. And now I deal with this system. If R is 0 for any pair, then I'm sorry, here is Gi and Gj. So if S polynomial can be reduced to 0 for any pair, then we know that this is a Grosvenor basis. If we have a non-zero reminder, then we add it to our system, and we compute S polynomials for this bigger system. But when you compute these S polynomials for this new system, of course, if I have tried these two polynomials, for example, then I should not correspond it one more time, because either I have seen that this can be reduced to 0, or it can be reduced to some polynomial R which have added to the system, and then by R I can reduce it to 0. So if I have corresponded this pair one time, then I should not correspond it one more time.
I have a question.
Yes.
So if we have added the R to our system and then try all other pairs, does it prove that the initial thing is a Grobner basis?
No, initial is not a Grobner basis
Yeah.
if we have a non-zero R, but this one then a Grobner basis. Maybe this new system is not a Grobner basis, then I have one more non-zero
R to
reminder
add there, yeah.
and I added.
Okay, I see.
Okay, let us do it with our system. First of all, either for standard lexicographical ordering, I have two polynomials x, y minus 1. This is g1 and g2, which is equal to, let me see, yz minus 1. So I need, first of all, my ordering. Now I should think that x is bigger than y is bigger than z. Okay, and I would like to compute leading terms. Of course, leading term of g1 is equal to x, y, and the leading term of g2 is equal to y, z. Okay, now I want to compute the lowest common multiple of these two monomials. Okay, it should be x, y, z. And now I should to compute as polynomial of these two polynomials, g1 and g2. So it's equal to x, y, z divided by xy, which is of course z, multiplied by, I'm sorry, g1 minus x, y, z divided by yz, which is x, of course, multiplied by g2. So it's equal to, where it is, z g1. So it's equal to x, y, z minus z minus x, y, z. Here is minus, I'm sorry. And minus x. Okay, this is x minus z. Now, of course, not only for this ordering, but for every ordering, I cannot reduct this guy because these two polynomials, g1 and g2, they are quadratic and its leading terms are quadratic. So this is multiplication of two variables. But this polynomial is linear, so it cannot be reduced anyway for any ordering. This shows that my first system, G1 and G2, is not a zero basis. Is not a Grobner basis, I'm sorry. So x minus z is already a reminder, and now I correspond this system, G1, G2, and G3, which is x minus z. Okay, what shall I do now? I need to compute S polynomials and try to reduce it to 0 or to remainder. Which S polynomials? S polynomial S of G1 is and G2 I should not consider because I have considered it here. And now I have x minus 0, and it can be reduced to 0, of course, by this polynomial g3. So if I have considered it, I shouldn't do it one more time. This is not needed. And I should to consider two as polynomials, S of G1 and G3, and S polynomial of G2 and G3. And I should try to reduce it to 0 or to remainder. Okay, let me proceed, but on the next frame, I have here G1 is equal to x, y minus 1. G2 is equal to yz minus 1. And G3 is equal to x minus z. Now I need to compute the leading terms. I have considered that this is the leading term of G1, this is the leading term of G2, and of course x is the leading term of G3. Now for S polynomial of G1 and G2, I need to compute lowest common multiple of G1 and G3. Of course, not G1 and G3, but their leading terms, I'm sorry. Okay, this is, of course, X, Y. Good, now I compute S of G1 and G3. This is just x, y minus 1. This is G1 multiplied by 1 minus y multiplied by x minus z. So it's equal to yz minus 1. But this is just G2. And of course, it can be reduced by G2 to 0. Okay, this S polynomial can be reduced to 0. And one more, LCM of leading term of G2 and G3 is equal to yzx, xyz. Now I can say that S polynomial of G2 and G3 is equal to xyz divided by yz multiplied by G2 minus xyz divided by x multiplied by G3. Okay, this is x G2, so x, y, z minus x minus yz multiplied by G3. This is minus x, y, z and plus y z squared. So it's equal to yz squared minus x. Okay. And now I want to reduct it by, for example, G2. By G2, this term is divisible by the leading term of G2. So I would consider yz squared minus x minus z multiplied by G2, which is equal to yz squared is common, and it is with 0 coefficient. So minus x plus z. And now I want to reduct this one, but this is just minus G3. So of course it can be reduced by G3 to 0. Okay, now I see that all the S polynomials of this system of 3 polynomials can be reduced to 0. And I say that this is the Grosvenor basis. A Grosvenor basis, because it's not unique, of course. But the first system, G1 and G2, which is given to us, this is not Grosvenor basis, but we add an extra polynomial G3, and now it is Grosvenor basis. Okay, was it clear?
Yeah, everything is super clear.
Okay, thank you. It would be very good if not one person would communicate with me. For others, so this is also clear, or you have some questions?
It's
Yep.
a bit hard.
Yeah, it's clear.
Thank you very much. Okay, let us proceed with number 3. Number 3, we have the system of 2 polynomials in ring of polynomials in 3 variables. We want to show that this is a Grosvenor basis for one lexicographical ordering, and this is not a Grosvenor basis for another lexicographical ordering, and we should to apply Buchberger algorithm and obtain a Grosvenor basis for this second ordering. Just the same, we need to compute all the S polynomials, and we need to try to reduce it to 0 or to remainder. But I should remind that, sorry, let me just these two guys, x squared y minus y squared. This is G1, and G2 is equal to x squared z minus z squared. As polynomials are depend on ordering, of course, because leading terms are depend on ordering. Okay, first of all, we want ordering z, y, x. So z is bigger than y is bigger than x. Okay, we compute just what is the leading term of G1. when z is the biggest and y is bigger than x, then this is leading term minus y squared. And leading term for G2 is equal to this minus z squared, because z is bigger than other variables. Okay, now we can we have a fact which we can use. I should just some computations, but there is the following theorem. It's rather useful. If greatest common divisor of two leading terms, L of G I and L of Gj is 1, so they are relatively prime. Then their S polynomial can be reduced to 0 just by these two, G1 and G2. Okay, if we use this theorem, then we have these two polynomials. Their leading terms are minus y squared and minus z squared, and they are, of course, relatively prime, and so this is a Grosvenor basis. But let us just do it by our hands, not by this theorem. We have lowest common multiple of minus y square and minus z square is with coefficient 1 y square z square. And now as polynomial of g1, g2 is equal to y square z square divided by minus y square multiplied by g1 plus minus y square z square divided by minus z square multiplied by g2. This is equal to minus z square g1, and this is minus x square y z square plus y square z square minus, and here is minus y squared multiplied by g2. So it is x square y square z minus y square z square. So this is just 0. And I should not reduct. This is also already 0. And now I have that G1 and G2 is a Grosvenor basis for this ordering. And now we change ordering and try to understand why it should not be a Grosvenor basis for another ordering. Now we have standard lexicographical ordering. So I have G1 equals to x squared y minus y squared. G2 is equal to x squared z minus z squared. And we have ordering x is bigger than y is bigger than z. Okay. First of all, we would like to obtain leading terms. Since x is the biggest, the leading term of g1 is x squared y. And the leading term of g2 is x squared z. There is no minus. Okay, now we compute the lowest common multiple of x squared y and x squared z. This is just x squared yz. And we compute the S polynomial of g1 and g2 by the following. This is x squared yz divided by the leading term of g1 is x squared y multiplied by g1 minus x squared yz divided by the leading term of g2, it is x squared z multiplied by g2. Okay. This is z g1, so x squared yz minus y squared z minus g2. This is minus x squared yz plus y z squared. Okay. This is not 0 because here is minus y squared z and plus y z squared. So it is equal to y z squared minus y squared z. Okay. Now we want to try to reduce it to a remainder. But there is no term with x in this polynomial, so there is no term which is divisible by the leading term of g1 or g2. So it cannot be reduced, and we just say that this is g number 3. Okay, and now we should try to obtain S G1 G3 and S G2 G3. Okay, the leading term of G3 is minus y squared z because y is bigger than z. So we can compute that this guy is equal to, first of all, lowest common multiple of x squared y minus y squared z. Of course, it is x squared y squared z. When I divide it by x squared y, I obtain yz. So it is yz g1 minus, I divide this x squared y squared z by minus z squared y squared z, and I obtain minus x squared. So here is minus x squared multiplied by g2. Okay, yz g1, it is equal to the leading term should vanish, so this is minus y cubed z plus minus, I'm sorry, uh, I'm sorry, here is G3, and this is minus x square y square z. I'm sorry, not
Y squared.
x square with plus. Here is plus x square y z square. Now it's okay?
Maybe. I cannot do it like all these operations in mind, but it looks right.
Okay. Now this is, let me think about it. Okay, just let me compute it in correct way. It seems that there is a mistake. I would better compute in more precise way. Y square z multiplied by g1. This is x square y square z minus y cubed z plus x squared multiplied by g3. So x square y z square and minus x square y square z. This is just the same with opposite signs. And now we have, it was okay. I'm sorry. It was okay. This is x square y z square minus y cubed z. So now I just try to reduce it by my three polynomials. For example, I want to choose this term and reduce it by the first polynomial. Just x square y z square minus y cubed z minus g1 multiplied by z square. So z square g1, the leading term is the same as here, and they are vanish. So minus y cubed z minus, or just plus, z squared y squared. Okay, and now I cannot reduce it by g1 or g2 because there is no excess, but I can reduce it by g3. For example, for this one, I can say that this is minus y cubed z plus z square y plus or minus y G3. Here is square. And this is just 0. Okay, we have checked that this S polynomial G1 and G3 can be reduced to 0. And the last, I hope, guy is that S polynomial G2 and G3 can be reduced to 0. Now I should compute the lowest common multiple of the leading term of G2 is x squared z, and the leading term of G3 is minus y squared z. Okay, what is it? This is just x squared y squared z. And now I compute that this S polynomial is x squared y squared z divided by x squared z multiplied by g1 minus x squared y squared z divided by minus y squared z multiplied by g3. This is just yz g1 minus plus x squared g3. This is g1 is x x squared y squared z minus y squared minus y cubed z plus, where is g3, y z squared x squared y z squared minus x squared y squared z. These two guys vanish, and we obtain x squared y z squared minus y cubed z. Now I should try to reduce it, for example, by g1. Where am I? Oh, I have a little bit problem. Here it is. I'm sorry. Okay, I would try to reduce it by g1 with this term. Let me remind that g1 is equal to x squared y minus y squared. Yes? Yes. And I should say that it is x squared y z squared minus y squared z plus minus z squared multiplied by g1, and this is equal to minus y squared y cubed z plus y squared z squared, and it is divisible by g3 so it can be reduced by G3 to 0. Now we obtain that for our system G1, G2, and G3, we have that all the S polynomials can be reduced to 0, and for this ordering, we have that G1, G2, and G3 is a Grosvenor basis. So this task is very vital because we understand that we have a system which is Grosvenor basis for one ordering, but it is not a Grosvenor basis for another ordering. Okay, it was rather hard with computations, but we managed. And now let us solve the fourth, and it should be all for today. We are given by system of equations. Let me just put it down. These equations are x plus y equal to 1. And another one, x squared plus y squared equal to 2. Okay. And we would like to compute, sorry, I have zoom here. We would like to compute the value of x cubed plus y cubed. In order to do that, we proceed with the following steps. For example, first of all, we compute the Grosvenor basis for these two polynomials. Okay, we want to compute these two polynomials, so we have polynomial G1 is equal to x plus 1, y minus 1, and G2, which is equal to x squared plus y squared minus 2. So of course, this system is just system G1 equal to 1, to 0, and G2 equal to 0. And now we want to compute the Grosvenor basis of these two gains. The leading terms, x and x squared. So as polynomial, of course, lowest common multiple of x and x squared is equal to x squared. And we have that as polynomial of G1 and G2 is equal to x squared, let us say that x multiplied by G1 minus G2. Which is x y minus x minus y squared plus 2. Now we will try to reduce it. It is not. It cannot be reduced by G1 by G2, but it can be reduced by G1. Just for example, this one. Then I say that this can be reduced to y squared minus y minus x minus y squared plus 2. Is there a mistake? Here is minus and here is plus. I'm sorry, because I should take g1 with coefficient minus y. Okay, this is equal to minus x plus y minus 2y squared and plus 2. And now we can reduce it either by g1, but with respect to this term. Okay, we just add g1 to this polynomial and we obtain 2y minus 2y squared plus 1. Okay, and this is
Plus
the
one?
reminder.
Isn't it
What?
plus 3?
Here is minus 1 in g1.
Oh yeah, and we use plus, okay.
Okay, and this is just a reminder, and this is g3. Okay, and now we should compute the reminders of g s g1 and g3 and s g2 and g3. But I understand that they all can be reduced to 0, because what is the leading term of g3? This is minus 2y squared. And here in g1 and g2, the leading terms are x and then x squared. So the leading terms are relatively prime. And I can use this theorem, this one, and say that as polynomials they must can be reduced to 0. So now g1, g2, and g3 is a Grosvenor basis. Okay, the point B. We compute the remainder of x squared plus y squared with respect to g. Okay, let us do it. We have a polynomial f x squared plus y squared. We have g1, which is equal to x plus y, x plus y minus 1. g2, which is equal to x squared plus y squared minus 2. And g3, which is equal to y 2y minus 2y squared plus 2y plus 1. Okay. I want to take f and to have a reminder of f by these reductions. So first of all, I see that x squared, for example, is divisible, x in the third is divisible by x squared. So let me try to reduce by g1. So I say that it is x squared plus y, x in the third plus y in the third minus x multiplied by g2. This is equal to y squared, y in the third, y cubed, minus x y squared minus 2x. Okay, now it can be reduced by g2, but it can be reduced by g1, for example, with respect to this one. Okay, let's do it. It is y cubed minus x y squared minus 2x plus y squared g1, which is equal to y cubed minus x y cubed minus 2x plus x y cubed plus sorry, okay, here it is. And now this and this is 0, and I obtain 2y cubed minus y minus 2x. Now I can one more time reduce by g1 for this term. So this is 2y cubed minus y minus 2x plus 2g1. So plus 2x plus 2y minus 2. And this is 2y cubed minus or plus y minus 2. Okay, and now I want to reduce it by g3. First of all, for this guy, and now I reduce it by g3. This is 2y cubed plus y minus 2 plus y multiplied by g3. This is minus 2y cubed plus 2y plus 1. And I have a problem because I have obtained 3y minus 1. And they say that this must be a constant. Let me think about it. If I have a mistake.
Shouldn't it be in the first reduction plus 2x?
Yeah, it should be. In the very first one.
In the very first one, yeah. Y cubed minus x y squared plus 2x.
There is minus minus.
I think about it. I'm sorry.
There is x cubed plus y cubed minus xg2, and this would obtain plus 2x.
Yes, of course. You're right. Here is plus. Here is plus. Here is plus, minus, minus, plus. I'm sorry very much. And this is here is minus. And here's plus. It seems that this way, here is minus, plus, and so on. I'm sorry, there is a mistake, and it seems that the time is over. So let us proceed tomorrow from this. I shall see what is the problem with this computation, and from this place we proceed tomorrow in our extra seminar.
Also, can you just send the link to this Jamboard in the chat?
Link. I have not do this. I'm sorry. Where is chat? Here it is. This is the link for Jamboard. Okay, I'm sorry for this mistake, but tomorrow I hope we can find it. And now, thank you very much. And if you want, there is a consultation by link in Wiki, on Wiki page. There is a link for our consultation. Okay, thank you very much.
Thank you. Goodbye.
Goodbye.